All right, this is section 5.3 in the book. This bravado sounding name, fundamental theorem of calculus. Whenever you hear something's a fundamental theorem, at the very least, you got to give it credit. It's going to be important. Does anyone know the fundamental theorem of arithmetic? I guess I'm testing the quality of education in your high school. Anyone heard of that? No. Fundamental theorem of arithmetic just says if you have an integer, you can break it down into prime factors. And you can only do that one way. Not important knowledge, but not on what we're going to worry about. Fundamental theorem of algebra. Fundamental theorem of algebra is? No. Well, I'm going to give you the actual fundamental theorem of algebra, not the one that in my head, I think it is. You have a polynomial. Polynomial equation like this. Fundamental theorem of algebra says it has a root. That's actually all it says, it has a root. Now, that doesn't sound that useful until you realize if it has a root, like r, and you divide it by x minus r, you'll get a polynomial of degree 1 less than n. And that polynomial has a root. So if you follow this through logically, any polynomial of degree n has n roots. That's what I usually think of as the fundamental theorem. It's not. It's just it has a root. Okay, so we've been dancing around the fundamental theorem of calculus. It's the connection between integration and differentiation. And there are actually a whole bunch of these, depending upon the environment you're in. If you make your way to calculus 3, there's a fundamental theorem related to multivariable calculus. But the version that the book provides comes in 2 parts. First part, it looks like this. We create a function using integral. Well, we start with some function f. And we create a new function by integrating from some constant to x for this integral. And we call this f of x. And the fundamental theorem, part 1, says that we have this, then the derivative with respect to x of this function is just equal to little f of x. Well, this is what we've been looking at. We found that when we want to find an integral, we find its antiderivative and we evaluate it across those parameters. So this is not, it's not that different from what we've looked at. Part 2 says that if you have some function, we'll call it the antiderivative function, and we'll find the derivative of it, we get some function f of x. If that's the case, then we can evaluate the definite integral of this function as the antiderivative at the two limits, the difference between derivative at the antiderivative at two limits. So this is actually more of what we've been using to find area under a function. All right, now, if I gave you a problem like this, I said, well, I have some, we'll throw something in. And I want to find the derivative of this. This is kind of a tautological here. So what would this equal? This again, it's a function, so I expect the derivative to be a function. Well, the first part tells us, it says here f of t, little f of t is sine of x. This interval here is big F of x. And it says the derivative of big F of x is just little f of x, it's just sine of x. Now, if I were to tell you that I have some function f of x, and its derivative is little f of x, what would the derivative of f of x squared be? Sounds a little like a trick question, but it's not. If you remember the chain rule. See what that has to be.
X squared over 2x.
I couldn't quite hear the first part.
X squared over 2x.
And you said over 2x. You mean over 2x? But times 2x?
Oh, yeah. Times 2x.
Yeah, times 2x. Where does that 2x come from?
Derivative of the inside.
Yes, the derivative here. This is a chain rule, right? I wanted to go through this first so that I take my first example. And I change this to x squared now I no longer have sine of x, do I? I have sine of x squared times 2x. Again, that's just a chain rule working there. And just give it one more level of abstraction here. I have d dx from a to, let's call this g of x. What's this? This is f of g of x times g prime of x. Again, that's just that component that the chain rule gives you. So it's good to know this if you're given a question like this. What's the derivative of this function here? Okay, I think I'm going to want to leave these up here. Work over on the right for a minute. I guess I've described this in kind of a dry, kind of, algebraic manner, but I want to emphasize that this is that it's that connection. I have some function, say it's distance by time, some object is moving, and I find its derivative, right, because it's moving at a constant rate, and that's my velocity. So going from here to here, find the derivative with time. Now, I want to see how far I've traveled. Find my my integral from a to x, whatever, of this function, and that gives me back, my location, my distance. And without this connection here, it would be very difficult to evaluate integrals. We have to rely on some kind of limit, that we looked at, breaking up the area into little pieces and finding some limit, which, again, just happens to turn out this way. All right, so this will be a little bit of a review, but I just want to kind of plaster up here some basic knowledge that we have because of this. This should be pretty familiar by now. I find the integral x to the n dx, and I'm just going to express these as indefinite integrals for the time being. I hope we all know how to go back from an indefinite integral. If we have specific limits, we can make it a definite integral. This is the reverse power formula, and of course we need some constant there. We have 1 over x. This doesn't work for -1. So for -1 we need a special formula. This is the natural log of x, but we need the absolute value because we can't find the log of a negative number. we have kind of the identity operation here in calculus. We find the integral of e to the x, we just get e to the x plus c, and if we find the derivative, we're back where we started. We have I guess I could call this could be like the one cycle. Find the integral, you get the function back. Cosine is sine of x plus c. This is kind of a 4 cycle. Cosine, sine, sine, negative cosine, negative sine, and negative cosine. It's kind of a 4 cycle. And since I've mentioned these cycles, there's a 2 cycle. Is hyperbolic sine. Is the hyperbolic cosine. And vice versa, the hyperbolic cosine will be sine. So we have these basic building blocks. We can build a few more tools that are going to be useful in evaluating first one I want to point out is if I find the derivative of log of some function, okay, that we know that's 1 over the function times the derivative of the function using the chain rule. So that gives us this pattern to look for when we're looking at intervals. We see something that looks like this, where we have the derivative over a function. We can evaluate that. Again, we need the absolute value signs to make sure we get a positive log. But we have a nice formula here that we can use to look at, look for an easy way to find the antiderivative, find the definite integral. Here's an example, a simple one. So I'm given this as a problem. There are other strategies to go at this, but the quick one here is to notice that derivative of x squared plus x plus 4 is just what we have on top, 2x plus 1. So that tells us immediately that this is log of x squared plus x plus 4 plus some constant. Okay. So this is a nice pattern. That's a nice thing to know. It can be useful. We can go a step further with it. If we have f prime of x think about it, let's think about it backwards. If I wanted to find the derivative of f of x of the n plus 1, I'm sorry, log of f of x to the n plus 1, well, what would that be? That would be 1 over, I guess I did that wrong. What do I want here? I got this on n. I would have f of x to the n times n minus 1 times f of x to the n minus 1. There's something wrong. I'll come back to that when I figure it out. Sorry about that. All right, here's another example where this pattern would come in. Well, I guess this is an example of what I'm trying to do here, isn't it? Let's just try this, see if I can learn something from this. I know what this integral is. Well, I look at the derivative of x squared plus 1 is 2x. So that's going to be my f prime here. Well, why don't we just I'm going to have to bare my knuckles and think this out. If I find the derivative of, I want to find the derivative of 1 over x squared plus 1. How would I do that? Well, use the formula we have for 1 over a function. So that would be minus 1 over the function squared times its derivative, which is 2x. So that would be minus 2x over x squared plus 1. Well, how does that differ from this? We have a factor of negative 2. So if I make this negative 1/2, x to the x squared plus 1. Negative 1/2, 1 over x squared plus 1. And when I find this derivative, I'll be back. All right, so what did I learn from that? Let's see if I learned anything from that. Seems like if I have some function to the n, the factor I'm going to need here is negative 1 over n minus 1, right? And I'm going to be left with f of x to the n minus 1. Okay, that's what I was trying to show before. Let's check this. Let's check to make sure that that's actually right. That would be a useful formula if it were. That's the kind of nice thing about finding integrals. If you go through some process, you use some strategy, there's a bunch of them, and you're not sure, you can do something straightforward. You can find the derivative and see if you get back what you were looking for. All right, so let's find the derivative. Negative 1 over minus 1 times 1 over f of x n minus 1 plus c. All right, this is a constant. That's going to be 0, right? So that's all good. So what's the derivative of f of x to the n minus 1? Well, it's by the power rule, it's going to be f of x to the n minus, well, I guess it'd be better if I wrote it this way. So it'll be f of x minus n minus 1 minus 1 times the derivative of the change. So let's negative n minus 1, just f of x or minus n, so it's just 1 over f of x to the n. Okay, n times oh, but we have to multiply that by we have to multiply it by negative n minus 1 as part of the chain rule, as part of the power rule. So this goes away. All right. My confidence in calculus restored. All right. Any questions about this so far? No? Okay. I have an example for this using these formula. I guess I can just leave. I can just leave this one out. You may, if you have a good memory, know how to do this correctly. Want to find the integral of the secant of x times the tangent of x. Now, it so happens that we're supposed to know that. Anyone recall what that's supposed to be? The formula we had, or rather, we have something that if you find its derivative, you'll get this. Comes to mind? All right, maybe better. What we're going to do here, we're going to convert this to sines and cosines. So the secant is 1 over cosine. And tangent is the sine over the cosine. So what we're looking for is derivative of the sine over the cosine squared. Okay, that should make you think of this formula here, right? Let's make it a little clearer. Let's put a minus here and here. To derivative of the cosine is the sine. So we're in line to use this. All right. Well, better be careful with these minuses here. This is the minus outside the integral. This is the minus that comes from the formula. N minus 1 here, well, n is 2, just 1. And we have 1 over cosine of x, 2 minus 1, it's just that. Okay, these cancel. So it's 1 over cosine of x, which of course is secant of x. And let's not forget our constant. So if you recall, the derivative of the secant is the secant times the tangent. So we could have gone there directly, but again, using this formula, we can see how we use the formula. All right. I think we should write this pattern down here. We can find something else useful like this. We recall the derivative of the inverse sine of x. Yes, this is probably one of those you would put on a cheat sheet. It's a little tricky to remember, but up. Yes?
Is it 1 over root 1 minus x squared?
Yes, it is. So from that, does anyone recall how we found this? Just thinking ahead to the, it's not like we put something like this on the final, but you might recall that we have this formula for y dx equals 1 over dx dy. That is, if you want to find the derivative of an inverse function, it's 1 over the derivative of the function, and you have to convert back your variables. Okay, so we immediately know that the derivative of 1 over 1 minus x squared is the inverse sine of x. Well, this also suggests a formula. We want to find the integral of 1 over square root of 1 minus some function of x squared times its derivative. That's just going to be the inverse sine of that function. So we would have to identify those components in order for this to work. So let's take a look at this example. X over square root of 1 minus. Minus x to the fourth. Is x over square root of 1 minus x squared squared. Well, we look at x squared, it's 2x. So this kind of looks like f prime here. This is f. Well, really it's, if I divide by 2, this is f prime here, right? It's just f prime over 2. Rewrite this as 1/2. Did I do that right? Yeah, I want 1/2 here. 2x over square root of 1 minus x squared squared, which is exactly, where is it? It's exactly the pattern I'm looking for, where f of x is x squared. So I can just write down the answer, inverse sine of x squared plus c. All right, there's a lot of this kind of pattern matching and finding integrals. It's not like differentiation where it's just a straightforward process. So it takes a little looking ahead, a little creativity, a little experience. Right. So I want to write that one down here. The integral of prime of x over square root of 1 minus of x squared equals inverse sine of x plus c. Okay, before we try one more of these. Anyone recall what the antiderivative of 1 over 1 plus x squared would be? Or thinking backwards, what do I find the derivative of to get this?
X.
Yes, sorry.
Tan X, was that what you were gonna say?
Huh?
No. Okay.
Oh,
It's tan inverse of X. Well, once again, that suggests the formula here. Prime of X over 1 plus prime of X squared. That's going to be the inverse tangent of f of X plus C. No prime there. Again, if you just use the chain rule on this derivative, you end up here. All right. Okay, so let's try and use this in an example. This is a real differentiating example. Can actually find a definite interval here. Two 2t squared plus t squared plus the square root of t minus 1 over t squared t. Well, there's a kind of a sub-lesson here, which is it's often a good idea when you can to simplify before you try and integrate. So let's go ahead and do that. So from 1 to 9, we've got 2 the square root of t. Maybe this isn't a good example of this. I guess not. It's just an example. All right, that's fine. Right. Well, now I just need to use my power rule here. This is t to the 1/2, t to the minus 2. So I'm going to get 2t plus t to the 3/2 over 3/2 minus what? T to the minus 1 over minus 2 from 1 to 9. Okay, now it's just algebra. 18 plus t to the 3/2. That's everybody. You do that in your head? Square root of 9 is 3 cubed is 27 over 3/2. Just times 2/3. Let's go away. 1/9. Okay, so plus 1 over 18. That's the first part. Now we have 2 plus 3/2 plus 1/2. All right. 2 plus 3/2 plus half. This is 2 plus 2 is 4. 4 plus 18 is 22. 3 divided into 26 is 9 times 2 is 18. So that's 40 and an 18th, I guess. I think I did that right. But, all right. All right. So, we're going to take a brief look at an idea that comes out of the fundamental theorem. It's not very different. Kind of a conceptual difference that may be helpful. We start this way. We look at the fundamental theorem, where we have some function, the antiderivative of some other function, and we write the integral a to b of a function is just, we can evaluate by finding the value of the difference of the antiderivative at those points. Well, we could rewrite it this way. We can just substitute here antiderivative, derivative. And now we just have one function mentioned here. Its derivative and the integral of that derivative. You have to think about this a little. So what does this say? It says to evaluate the function at 2 points and find the differences. You find the net change of that function. That's where this net change comes in. You can evaluate that by integrating its derivative. Now, this isn't really different from what we've been doing. It comes across a little different. An example may help. Let's say I have a reservoir and it has some kind of outlet. And we have some function v of t is the amount of water in the reservoir. Right, so water is draining out at this point. So if we evaluate v of t2 minus v of t1, what's that? This is the level of t1, and this is the level of t2. What does this tell us? This tells us how much water is drained out. The net change in the volume of water. Well, this net change theorem tells us that well, maybe we don't have, like we would have on a beaker, we don't have a set of numbers here to tell us, to measure this. Instead, we could measure this net change by integrating from t1 to t2 the change in time. That is the rate at which water is flowing out. about that. It's flowing out 1 gallon a second for a few seconds, and then 1.5 for a few seconds, and a quarter. You just measure that outflow. You add it all up, and it tells you the difference in the volume over time, between these 2 points in time. So that's how you look at this net change theorem. There are other examples. The obvious one is when we talked about a lot in class. You're driving along in a car. My little our diagram here, and there's some kind of displacement over time for that car. And you have an odometer you can measure this with. That's one way to measure it. But alternatively, I'm going to actually try and make this look. I don't really know what this looks like here. If you take a velocity diagram, take the velocity where you watch the speedometer, and for small intervals, you multiply the velocity, you integrate it. You can also figure out where you are, what your displacement is. Now, this diagram kind of brings to mind something. Here I'm going forward, and here I'm going backwards. Sometimes I'm interested in where I am, which is the displacement. And sometimes I'm interested in how far did I travel, which are 2 different things. If I were to plot my velocity as such, over time. Well, I have 3 distinct areas here, area 1, area 2, and area 3, which they're not areas, they represent distances traveled. If I'm interested in where I am, then I'm interested in A1 minus A2 plus A3, right? That'll tell me where I am at the moment. If I'm interested in my displacement, how far have I traveled, then I actually just want A1 plus A2 plus A3. Or if you think of, this is some function, like v of t, this would be represented by the integral from, say, 0 to a of f of t dt. This would be represented by what? The absolute value. This is a problem I think we've looked at before. How do you find this? How do you evaluate this integral versus this integral? So why don't we look at a particular example that demonstrates that? So in this example, we have a particle velocity of t squared minus t minus 6. And first thing we want to know is the displacement as it goes from t1 equals 1 to t2 equals 4. So without even looking at what this, what the graph of this is, we don't really need to know. We can just find this integral. And that should be fairly easy to evaluate. Should be e cubed over 3 minus t squared over 2 minus 6t, 1 to 4. So what do I get? 64 over 3 minus 16 over 2 minus 24. First part, minus 1 over 3 minus 1 over 2 minus 6. I'm going to bring forward my minus here, minus, plus, plus. Okay, so 64 thirds and 1/3 is 65 thirds. That's 21 1/3. This is minus 8, minus 24, it's minus 32, plus 6 is, I have to do that again, 8, minus 8, 32, minus 6 is 26. Half, and I guess I have to convert everything to sixths here. 32 sixths plus 20, 156 sixths plus 3 sixths. 192, 195 over 6, or 32 and right. Try that again. 3, 3, 6, 2.5. It's never what I count on. Just want to see whether my notes are wrong or I'm wrong. Let's see. You need to realize this calculator, if you just, your axes are in the wrong place, it doesn't give you the right answer. Okay, negative 4.5. Not even close. Well, say that's, oh, yeah, these were much, all right, I'm not going to do the calculation. I'm sure you can do this. The more interesting problem, of course, is if I want to find how far the particle has traveled. So what am I going to need to do to find that? Well, we have to find out where the function changes from positive to negative. Sorry. How would we do that? Thoughts on that? When I find out where this function is equal to 0. Different. In a car, and I'm traveling along a straight road. And I can't turn around. I can stop and I can put it in reverse. So and what's worse is my odometer is not like a regular odometer. When I'm going forward, it goes forward. And when I go backwards, goes backwards. And I don't really want to find my displacement. That's what my odometer would tell me. I want to find the total distance traveled. So I got a pad of paper. I can write down what's on the odometer. What do I need to? What data do I need from that odometer so that I can add up these segments here? Traveling. Guess you could say I'm concerned in this trip about tire wear. I want to know how far my tires have gone, how far they've hit the road. What do I need to know? Yes, Lillian.
I'm not sure, but is it like finding the distance per each section? And then adding, so like
Speak up a little. Finding the distance.
for each section, for each segment, and adding them up.
Okay, that's what we want to do. Yes, we want to do that. But remember, I'm just in the car, right? I can read the odometer. I'm driving the car. What information do I need to write down so that I can make that calculation? Yes, it's not transparent, is it? All right, I'm going to write down some numbers. So my odometer starts at 0. to 60, no, not 16, it's more like 20. It goes to 60. It goes, somewhere along here it's like, say 45. Back here it's 18, and it's about 40. It's about 30, now it's 80, now it's back to 50, now we're 78. So, yes,
Using the absolute value, like, so there's no negative numbers. Using the absolute, like
I think I understand what you're saying, and I think you're right, you have it, but it's not clear to me, and maybe it's not clear to other people. Say again, speak as loud as you can, because I'm, what does my calculation look like? I mean, we could just do the problem. You just do the math problem. But I think you want to understand what's happening here. Nobody has any idea. But Lillian. Well, wouldn't I want to say, well, okay, 100 minus 0. That's my first segment. And then, see, 100, 20 minus 100. That's my next segment, here to here. And then 60 minus 20. And isn't this what you're talking about, Lillian? Just adding up these segments? Yeah, okay. So, what do I have to write down to be able to do this? I mean, get in my car, see my odometer is 0. I drive a ways. You stop. 100, right? I have to write that down. What am I writing down here that's important? I didn't need to write down 45 because I'm moving. And I have to write down where I'm stopped. Well, that's what you need to do. To figure this out, you need to know where the particle is stopped. Its velocity is 0. Because that's where the sign changes. We're only interested in positive values here, so. All right. Where is it 0? Someone want to tell me how to solve this? Yes.
T plus 2, T minus 3.
So you factored it. Okay. I know you know the answer. So Someone tell me what good this does me. Yes?
Do you know the zeros of the function?
Tell me what they are.
T equals -2 and t equals +3.
3, right? Okay, these are the numbers that allow this to be 0. Which ones do I care about for this problem? Yes. Yeah, this 3, right? 2 doesn't apply. So I want to break this up. Okay, so this is the displacement, and this is the distance traveled.
Yeah, that's what he's talking about. Why do you want to find out why it's because if you find the integral of the distance, it's just I think it's a very of the distance. Okay. Oh.
All right. That's all I've got for today. I'll post the homework assignment for the whole week after class, but I want to get working on it. You don't need to work on the second part.